So what? Oh, great. We give you the file and you run it. Typical Caroline.
It's Funyuns.
So we're going to read it as a class because it's awesome. Here we go on 3. 1, 2, 3. Particle time go. Alex is sad since it's hard. We know no try hard. That's the best particle physics haiku I've seen so far, but I haven't looked at all of them, so we'll have to see.
No, actually,
I'll pick some winners.
We put marks on the board too.
Say it again?
I think we should put marks on the board too.
I'm scared. I'm really scared.
Damn, I should have put on
If I will read marks, and if appropriate, I will put it on the board next time. Then after the whole
Can we just like
singing Valentine's Day, I gotta draw a line with Mark and his junk on that side of it. Anyway, all right. Okay, no, seriously. All right. So what we're going to talk about today is, in many ways, this is probably one of the most important ideas that we're going to talk about in this entire class. Because for many reasons, this set of ideas is what you use to connect particle physics to other areas of physics, and in fact, how you connect many different areas of physics, okay? So the thing we're going to talk about today is going to be in the context of what we've been doing in this class, but the results and the implications of those results go way, way beyond this class, okay? So I'm going to introduce sort of the technical side of it today, and then hopefully on Thursday we'll finish up the technical side and see how it points to other areas of physics and poses some very, very interesting issues to be explored. Okay, so I'm going to start with what I might call throwing this marker in the trash because it doesn't work. All right, I'm going to start with what I might call a classical fairy tale. And we will follow this in due time with a quantum fairy tale because, of course, this is physics. Why would you? If you do classical anything, you've got to turn around and do quantum something. Okay, so I want you to consider a muon sitting happily at rest. So there is a muon. There it is, folks. It's nice. It's nice. I drew that circle extra specially, symmetrically, circularly, symmetrical, spherically. Okay, so now suppose that this muon was just hanging out there and we decided that we wanted to measure its charge. And if you think it's a stupid exercise to measure the charge of a muon, let's just pretend this is some unknown charged object and I was interested in trying to measure its charge. Okay, so this should already sound weird to you, right? Because when in God's name does Alex ever talk about measuring anything? It's so silly. Okay, so classically, the way that we could probe the charge of this is we could take an object whose charge we already know. So for example, we could take an electron, and we could start this electron pretty far away and shoot it toward the muon. And then if we know various things about the electron, for example, if we know its energy and its momentum, but a nice way to parameterize it is if we know the energy of the electron, and we know the impact parameter. So that is, the electron's going to be zipping along that direction initially. Of course, it will deflect. And then the deviation from its trajectory and the actual center line trajectory with the muon is the impact parameter. And then we know what's going to happen. The electron's going to come in. When it gets, it's going to feel the electromagnetic repulsion from the muon infinitely far away, but it'll get appreciable the closer they get. And so we know what will happen. Eventually its trajectory will deflect. And then we can wait a while and measure the outgoing properties of the electron. And then what we can find out is that by measuring the scattering angle theta that our electron emerges at, we can use an expression that says the charge of the thing sitting here, which in this case is the muon, is equal to, and I should say in all of this we get to use an approximation, which we've already used in this context. The muon is hella big compared to an electron. So in this process, the muon, if it starts at rest, it pretty much stays at rest. So you can kind of think of this as a satellite. scattering off the Earth or due to the Earth's gravitational field. So in that simplified scenario where the muon doesn't move, then we have a simple relationship between the charge of the muon, the impact parameter, the energy of the electron, and the charge of the electron, and the cotangent of the half the scattering angle. We're not interested in, huh?
Alpha or 2?
That's a 2.
Squared.
That's a 2.
B squared?
Say again?
Is it squared?
It's what squared?
Like B squared, or is it B times 2?
Sorry. Yeah, no, 2BE. Okay? So this is a formula which you can derive. It's classical scattering theory. There's not a lot of really interesting stuff here, but just functionally, this is how we might go about experimentally determining the charge of this thing sitting right here. Okay? We probe it with something, much like the aliens in South Park. We probe the poor muon with a very high energy electron. Well, no, I'm just kidding. With an electron, and then we measure some things and we calculate the charge of the muon. Okay, pretty straightforward, right? Well, now let's take our muon and do something interesting with it. Let's take our muon and let's drop our muon into a dielectric. Okay? So one of the things we know about what's going to happen when we place a negatively charged particle like a muon in a dielectric is that the dielectric material is going to respond to it, and sort of a simplified model is we can think of these little charged dipoles with a plus and a minus end, and the positive end of each dipole is going to be attracted to the negatively charged muon, and so we're going to have we're going to have sort of a reorientation of the dielectric material. So before we stuck the muon in there, maybe things were random, depending on the temperature. Maybe there was some alignment induced by the temperature. But anyway, so we stick the muon in there, and all of a sudden these dipoles start responding. And I have to draw this a certain way for a reason you'll understand in just a minute. So I'm not like doing a Family Guy thing where they just take this joke and they make it unnecessarily long.
This isn't even a joke.
That's right. This is not a joke. This is physics. This is the best stuff in the planet. Period. End of discussion. Okay. So sorry, I just have to draw sort of enough to get the representative story out there. Okay. So we've got this sort of random material, and we stick the muon in there, and the material responds in like fashion. And then what becomes important, and a story that you're all familiar with, is if you want to start talking about experiments, okay, then it becomes very crucial to think in terms of not the charge that's there, but the effective charge that something sees. Okay? So we can ask, if I go out a certain distance from the muon, what's the effective charge that I see? And so we can use the standard electromagnetism construction. We just draw a Gaussian surface surrounding the charge. Centered at the muon, we calculate the net charge contained within that Gaussian surface, and then that's going to give us a value for the charge at that distance. And if we go further out, we can draw a larger Gaussian surface. And then if I did this right, what you'll notice is that you're actually going to get different values of the effective charge for these two Gaussian surfaces, because this guy has got the muon in it, and then it's got 1, 2, 3 positive charges. But if I go out this far, it's going to have the muon and 1, 2, 3, 4, 5, 6, 7 uncanceled positive charges. You don't include these pairs because they're completely contained within that Gaussian surface. Okay? So for the inner sphere, you've got shielding by 3 positive charges, but for the outer sphere, you've got the muon charge shielded by something like 7 charges. Okay? So what we find now is that if we run the same experiment and we shoot in an electron with some energy E and impact parameter B, that the results of the experiment are actually going to become very sensitive to just how close to the electron we're probing, okay? Because in particular, the higher energy we send the electron in with, the closer it's going to come to the actual muon. If we send it in with lower energy, it's going to deflect sooner. So a lower energy electron is going to see a greater screening. A higher energy electron is going to see a smaller screening. Okay? And so what we can kind of argue from this is that the effective charge of the muon is actually going to scale with sort of the distance of closest approach. Okay? So technically the effective charge scales everywhere because, along this whole trajectory you're seeing a different value of the charge. But we can just kind of pick one value to parameterize things by. So take the point of closest approach for any trajectory. And so the effective charge as parameterized by that point of closest approach, it's going to depend on what your point of closest approach is. Okay? If your closest approach is smaller, you're going to see less screening. Okay, so you'll see a different value. But of course you can trade this out for the Q being a function of the electron energy. Because again, the point of closest approach is going to be dictated by how much energy you give the electron. I'm assuming here that I'm using the same impact parameter for everything. Okay? All right. Everybody on board with this story? Something you should have seen at some point in one of your classes. Jacob.
So won't the polarization vectors of the dielectric material be, like, they're more polarized closer to the dipole?
Sure, yeah. This is just a cartoon. There's a lot of elements to this which are not entirely accurate. So I guess when most people talk about this, they're not putting in like a muon. They're putting in actually like some large macroscopic hunk of charge, and then you get an appreciable response from the material. In this case, it's hard to believe that a single particle carrying just an electron charge would create, and so I'm being sort of exaggerated here, but you'll understand why I'm using this You'll understand why I'm using this case in just a minute. Okay? Now, I should point something very, very important out in this context, and that is, okay, yes, we have this dielectric. We're trying to measure the charge of this. We find out that really what we'll detect is the effective charge, which scales with energy, but we have a method of determining the real charge, right? What is our method for determining the actual charge? Like, yes, I get this screening, I have this effective charge. I would really like to know what is the honest charge of this thing without any screening. What can I do?
Take it out of the dielectric.
Yeah, I can get it out of the dielectric. I literally could just do this. Okay? That might seem like a really silly observation, but it's going to become crucial in a minute. Okay? There's actually a second way that I can probe the true charge of the muon. What is the second way that I can probe the true charge of the muon within the dielectric?
Drop type of experiment?
How about get really, really close to it?
Yeah, if you get closer to the muon than any of the polar atoms or molecules or whatever the dielectric's made of, then you're not going to see any screening. So you could either remove the dielectric, or you could just probe this with sufficiently high energy, and at sufficiently high energy, you're going to see the true charge of the muon. Both of those observations are going to be incredibly important to keep in mind. Okay? All right, so what in God's name does any of this have to do with this class? Well, I'm glad you asked. Thanks for asking, Ashley.
You're welcome.
All right, so if we were to talk about a quantum version of this story, I spelled it wrong. I'm trying to spell it with the English F-A-E-R-E-Y. What's the effed up way you spell fairy? Anyway,
No, that's how it's spelled in English.
F-A-I-R-Y?
That's correct.
I.E.
Right?
Matt, how do you
No,
say
that's
fairy?
like the.
Look, you guys, I am not going to sweat being unable to spell fairy or sandwich for this class. I got bigger things on my plate.
How does he spell sandwich?
I actually, well, it's funny, the way I spelled it, when I went and actually looked it up, it was bad. It's like, it's a word, but it's bad. So it's one of those things, you just kind of want to get it right, because when it's bad, it's bad. Okay, anyway, all right, so what I want to do now is I want to draw the sort of quantum picture of what this looks like. So we sort of know there's an electron, and there's a muon, okay? And we're going to shoot the electron at the muon. Secretly, we know that this language is kind of crap because this is really a localized excitation of an electron field. This is a localized excitation of the muon field, but to a good degree, they're acting like particles, so we'll draw them like particles. And the electron is going to come in, and then the real picture in this class of what happens, we can think of as the electron feels the electromagnetic repulsion of the muon, but the mechanism for that is through the exchange of a photon. Okay? So this is the sort of quantum picture underlying this classical picture. Okay? But, and this is where it gets interesting, that is certainly not the only, what, Spencer? Yes.
Well, I mean, since it interacts technically everywhere, is it like an infinite number of photons interacting, or like, can you approximate it to one?
No, you don't approximate it to one. So it's, yeah, well, okay. Yeah, this is a, This is a really, I'm drawing a really fuzzy picture here, because one of the things we have to keep in mind is when we draw Feynman diagrams, we're not actually drawing particle trajectories through space. Even when we draw like these little vertices where they kind of bend, we're not claiming that that's, if you actually took like a bubble chamber and tracked the path of a charged particle, that it would do this kind of thing that you draw in front of. That's not what we're saying happens. It's more complicated than that. Those are just useful tools, but nonetheless, if you wanted to, so to answer your question is going to lead into my next point, but if I wanted to consider this process, which is literally, classically, these start interacting very far apart. Of course, the interaction, intensity grows as they get close together. To do this quantum mechanically, first of all, we really have to start with this at infinity, where it's not interacting at all. And we have to measure it when it's gone to infinity and not interacting at all. That way we can start with free particle and end with a free particle state. And then we can treat the interaction perturbatively. The leading order diagram is just this single diagram. You don't have to draw a bunch more, okay? Now that's leading order. There are other diagrams, which is the important point to make, and that is that in addition to this diagram, there are many others, but among them is one that looks like this. And this is not the way we usually draw Feynman diagrams. I'm just trying to sharpen the analogy to this picture, okay? So there's a diagram that looks like this. Okay? So while the photon is en route from the electron to the muon, it actually burps out a particle-antiparticle pair. Let's just keep this simple, basic QED, photons and electrons. So the particle-antiparticle pair would be an electron-anti-electron. Okay? But you recognize that this is an allowed Feynman diagram. It's built out of the same vertices that all QED Feynman diagrams are built out of. It's higher order than this one. Okay, this is technically a second order diagram because this would be drawn like that, and similarly here. Okay, and then this would be a fourth order diagram, but nonetheless, this would be a contribution to M. And then we could keep drawing more and more and more. Okay? Now here's the interesting observation. We have the electron, we have the muon, and between them we have a E plus, E minus pair. Granted, it's virtual, but there exists an E plus, E minus pair. So is there any reason not to suspect that they would respond in a manner similar to the dielectric? That is, this E plus and E minus virtual pair would have some, even if it's a very short-lived reorientation, so that they could effectively screen the charge of the muon. Okay?
Alex,
Yes.
screen the charge of the muon from a what? From the electron?
So, we're using the same setup we have here. We have the muon sitting there, and we're thinking we want to measure its charge. And we want to send in an electron probe. So let's pretend we know everything about this. The only thing we know about this is that it's sitting still, which we can safely assume because it's so heavy, and we just start it at rest, it stays at rest. And so we're treating the charge of this as an unknown. And the point in this context is you've got to be careful with the dielectric because the muon charge that you're trying to measure is screened. And so we could ask, is the muon charge in this quantum version similarly screened by these virtual pairs? Okay? Now, the answer to this question is that, in fact, there is a screening type effect. Okay? And, but what we can do is we can be quantitative. This is sort of the qualitative picture in analogy with this, but we have the tools under our belt to be quantitative, so let's actually look at the quantitative version of this. And by the way, this classical story of screening and effective charge, when it is rolled into the quantum version, is essentially the story of renormalization in quantum field theory. Okay, so we're now embarking on renormalization, which is this incredibly important and central idea that permeates a lot of different areas of physics.
Okay, wait, before we do that, maybe I just didn't understand your answer to Will's question, but...
To Will's question? Oh.
Yeah, the screening, the virtual pair is screening muon charge from the other electron line? In what sense is it screened?
So, well, the sense in which it's screening, so I will agree with you that when I draw this picture, it's not convincing.
Okay.
Is this convincing?
Yeah.
Good. This is not quite convincing. That's fine. This is a heuristic picture. I'm actually going to do some calculations.
Okay.
Okay. So it's fine if you're not. I like that you're not comfortable with this, and you should be begging me on your hands and knees. Please, please, please back this up with a big, huge calculation. Here we go. All right. And I'm actually not kidding about the big, huge calculation. This is going to be pretty ugly. And I will certainly make very large leaps where I feel like it is appropriate. So those of you who want more detail, I can send you a lot of resources. Okay, so the process that we're actually interested in studying is an electron muon goes to an electron muon. And fortunately, we have already actually studied this to some degree with QED. It was one of the processes that we started at first. So we know that the diagram, so I have my electron, my muon, okay? We know that we start calculating the amplitude for this M by drawing the simplest diagrams first, and then we just allow diagrams of increasing complexity. And the simplest diagram we can draw, which is called the tree level diagram, and I'm going to use some notation here, some language here that I might not have used before. But the tree level diagram is typically the leading order diagram, okay, in a Feynman expansion. And it's kind of called a tree level because it's got no holes in it. It's kind of like a tree. Like typically trees don't have holes. Some do, but that's an anomaly. Okay, so it's just kind of like it's stuff that's branching off. Now we're going to draw the second leading order diagram in a minute, but let me go ahead and remind you what the result of this calculation. Well, actually, yeah, I'll just go ahead and draw this. I'll draw the second leading order diagram. So there are several diagrams at next to leading order, but the one I want to focus on is the one that is analogous to what I just drew. Okay, where we're going to have, and now I'm going to put in some labels here because we're going to write down some actual expressions. So I'm going to have momentum 1, I'm going to have momentum 3, momentum 2, momentum 4. So I want to label these the same so that I can actually add the expressions consistently. Now for the internal momentum, I'm just going to do the following. So this is going to, I'm going to say that carries a momentum upwards of a value q. And I'm actually going to go ahead in this second diagram and use momentum conservation. Okay, so I'm going to say if I have Q going up, then that means in this branch up here, I also have to have Q. Because you can't really lose any Q to this bubble because the bubble appears and disappears. Like, it's got to be conserved. And then that means if I have, this is going to get ugly. I don't know why I did it this way, but I did. So I'm going to have my particle lines go that way, and then I'm going to have a momentum going along this edge of the bubble of value k. But that immediately tells me that the momentum on this edge of the bubble has a value k minus q. Is that me or you? Is it me? Oh, I'm getting... Oh, my girlfriend is texting. That's so sweet. She obviously doesn't know I'm teaching. Happy Cinco de Mayo. All right, anyway, where was I? Okay, does everybody understand this? Like, if you were starting out like day one of Feynman diagrams, you would call this Q1, Q2, Q3, Q4, and then you'd write a whole bunch of delta functions, 4 of them, and then you'd go back and say, oh, wait a minute, I was silly. I know this has got to be the same as this, and then the sum of these two has got to be Q as well. Okay? So I'm just kind of using that knowledge in advance. Okay. So what I really want is I want the M's for these. And of course, there are higher order diagrams. So the M is going to have a tree level contribution, which is going to be given by minus GE squared. And this should look familiar. Of course, as usual, I'm going to go ahead and do a few steps, like the delta functions, and then evaluating the integral with the delta function, and so forth and so on. So I've got 2 spinner sandwiches, the propagator, U bar 4, gamma nu, U2. Okay?
Hey, Alex.
Yeah.
Is it supposed to be Q minus K?
Where?
In the second order diagram. Q minus K, Q minus K.
On the right side of the circle.
The absolute value of whichever one's correct.
No, but it's going
So this is K minus Q momentum flowing this way. So for example, let's add up the momentum at this vertex. So I have Q coming in, I have K coming out, and then I have K minus Q coming in. So yeah, it's weird because the arrow, if I flip the arrow and had it go up, then it would be Q minus K. As long as you're consistent and the delta functions are put in place and to impose conservation of energy momentum, it'll work out fine. Okay, so this result should be familiar to most of you for the tree level contribution. Where it gets ugly is when we go to one loop. So I'll just write down the one loop contribution. And now is when you might take a nap. And I want to say something. Q, we know we could actually describe Q in many ways in terms of the external momentum. So if you wanted to, you could call this P2 minus P4. But I'm actually going to leave it as Q. And that's actually a sort of a nicer way to think about it, because we can just think about Q as parameterizing the momentum transfer. It's sort of like the energy scale of the process. Okay? So instead of having to make you think about, well, what was P2, what was P4, and what's their difference, I'm just going to work in terms of Q. So I'll leave everything with Q's whenever I can. And clearly Q is also the momentum transfer in this process. Okay? So the next leading order diagram is going to look like this. So that is a Q fourth. Fortunately, we get the same spinner sandwiches because when we trace the external lines here, we just get a line vertex line, same as we got here. So the spinner sandwiches is the same. Where it gets ugly is when we have to do all of this internal matter loop, and then the photon propagators and the extra vertex factors. I actually introduced this Feynman rule right at the end of our lesson on QED. It's what do you do when you have an internal loop of matter? Okay, and the rule was basically that you write down propagators for the matter, vertex, you do a propagator, vertex in order, some cyclic tracing of those things, and then at the end you trace over that expression. if you don't remember the details, that's fine. I just want you to have an idea of what I'm about to write down and why it looks the way it does. So we have D4K, 2 pi to the 4th trace. And then I have no idea where I wrote this with lower indices. Oh, because they have lower indices, actually. It just works out that way. And then we cap it with a spinner sandwich for the other lines. Okay, so before you get lost in the details here, let me just kind of go over what these things are. So there's a lot of constants that I've kind of massaged out of this, but this gamma mu I can think of as being one of these vertices. Okay, remember QED vertex factors, you put in a factor of IgE gamma mu. So this gamma mu is going to be one vertex, and then this piece over this piece is this propagator. And then I have another vertex, and then this piece over this piece is this propagator. Okay? Now, I don't have to put the denominator inside the trace because these pieces in the denominator are not matrices in spin space. The trace is over spin space, and so everything up here is the essential parts of the propagators and vertex factors that are non-trivial in spin space. Okay?
So didn't we learn for antiparticles it's minus MEC as opposed to plus MEC for one of those terms?
No, the propagators are the same. It's when you actually go and that's if you're trying to evaluate the spin averaged and summed m squared, and then you're going to replace certain spinner sandwich quadratics with expressions that are like the Dirac equation. And in that case, when you encounter a particle versus an antiparticle, there's a plus versus a minus for the MC term. But we're not even going to go to that step. Yeah, when you write down propagators, and go back and look at the Feynman rules for any theory, the propagators always look the same, whether it's a particle or an antiparticle. We don't care. Okay? All right. Now, this is just the first 2 contributions, but this is what we're going to spend our time focusing on. And you all now know, especially after this homework assignment, that this is just a number. Like right at the end of the day, if I gave you the energy and the masses and the momentum, you could actually plug in all of the information here and get a number out. This, on the other hand, is, well, what is this? Well, first of all, I hope you realize that there were 2 internal momenta, Q and K. All right? But I used the delta function to do the integral over Q, because there would have been an integral d4q over 2 pi to the 4th, but there's also a bunch of delta functions, and I could use those delta functions to do that one. However, I'm out of delta functions. This integral over K legitimately has to be done. Okay? Now, does anybody want to do that for me? No volunteers?
It's infinity.
Exactly, it's infinity. Good. So the problem is, let's just do a counting. Let's count the k's in the numerator. Okay, so d4k is secretly k cubed dk. That's the same way we can break up, for example, dv, if you use spherical polar coordinates, as r squared dr with some angular factors. So generally speaking, a d4k can be broken into a d3k the same way as a d3k can be broken into a k squared dk. And then I've got a k and a k. And in the denominator, I've got a k squared and a k squared. So at the end of the day, I'm integrating k dk. Okay? Now here's the question. What are the limits of that integral?
Yes.
Pretty big.
Well, I have to integrate over all possible values of k. Like there is no biggest value, smallest value. I literally have to do all possible values. Now you might look at this and say, well, you can only kind of have as much momentum as you have in this transfer q. But no, because this k and this k can be arbitrarily large. And momentum still be conserved in this diagram. Okay, so I literally have to take that from 0 to infinity. That's okay. No wonder you guys are looking at me like, what the hell should I know? Yeah, to infinity, sorry. Okay, so this is divergent. This is one of the fabled infinities in QFT. We encounter them all over the place, actually, when we go beyond leading order, typically. Okay. Now, it's actually not as bad as you think, because it turns out this was a really naive power counting. If you actually were to put in, more faithful expressions into here and evaluate the trace and so forth, there's some really nice cancellations that occur so that this thing ends up with a logarithmic divergence. But nonetheless, it still diverges. Okay, so there's an infinity, and that's a bit of a problem because we're trying to calculate m. We get a finite answer for the leading order term, and then we get infinity for the next order correction. So your answer is 2 plus infinity. That's not very good perturbation theory right there. Okay. So believe it or not, the answer to how to deal with this problem plagued quantum field theory for a long time, especially in the early part of the 20th century. There were people who were ready to give up on it and just were ready to say, you know what, this theory is just inconsistent. You're getting these infinities. We can't figure out how to interpret and handle them. Maybe we should just stop doing quantum field theory and do something else. Maybe this is not the right way to do it. There was a considerable amount of progress made in the 60s. In particular, the program that I'm about to lay out to you was developed around that time. Even then, people were still like, it kind of works. I see what you're saying, but I just don't have a firm appreciation of it. But it was really in the 1970s, this guy named Kenneth Wilson came along, and he really thought really deeply about what was going on in all this. And he really revolutionized our thinking. And we're going to talk a little bit more on Thursday about what Wilson did. Today, we're really just going to focus on sort of the systematics of what was done to address these infinities. Okay, so here's where I'm going to skip a great big old step. And I am going to call this thing right here, this integral, which bear in mind, this is a standalone thing because this is a spinner sandwich, it's a number. This is a spinner sandwich, it's a number. This is a spinner burrito, but it's a number. But it's an integral, so we have to do the integral. But nonetheless, and then this is obviously a number. So I'm going to take this whole thing, and I'm going to call this minus I eta mu nu times I of q squared. Okay? Now, there's a little argument you can go through. You can say, okay, well, if I look in this, it's got 2 space-time indices. So whatever I'm going to call this has got to have 2 space-time indices. Really and truthfully, there's only 2 things I could even tease out of this with space-time indices. That's the metric and then the indices on Q. So I could just build something like this. Okay, the gammas are spinners. They disappear when you trace. Okay, so these are the space-time sort of tensors that have those indices. And so if you literally took this thing and you evaluated using the QQ here, this whole term ends up evaluating to 0. So this is the only term that we have to worry about. Don't worry, there's a lot to that story that's not important. I just want you to understand that I'm going to call this thing minus I eta mu nu IQ squared, and then I'm going to do the following, which is after much massaging, and it's a lot, and if you're really curious in the details of this story, I strongly encourage you to go and look at where this, or how this plays out. The leftover integral IQ squared can be written in the following form. And really and truthfully, the details of this are not the crucial issue. I'm gonna point out the salient features, but if you're trying to write down every single term in this expression, it's really not going to be that meaningful. I didn't say you should leave, but you've got your priorities and I've got mine. I.e., I control your grade. Son of a bitch! All right. Okay, so so you can literally start evaluating this thing and massage it into this form. And we immediately notice, hey, look at that. There's our logarithmic divergence. Okay? But more importantly, what we find is that this piece right here, though not obvious, okay, is a finite integral. And we're just going to call it a function of minus q squared over m e squared c squared. So you could actually go and evaluate this integral if you had enough time, if you had enough techniques. But all that really matters is, first of all, this is divergent, this is not, but this thing depends on q. There's a q in there, and we're not integrating over that q. Okay? So what I mean by this is, this factor of q that appears here, the factor of q that appears here, that is basically this momentum exchange. This momentum exchange is going to be determined by how hard you send in the electron towards the muon. Okay? The harder you send that electron in, the more momentum it's going to exchange with the muon. So this q that this depends on, this is really sort of, it's gauging the energy scale at which you're performing this experiment. Okay, so it's going to be an important thing to track. Now, the only thing you really need to know about this function is that f at q squared equals 0 is itself 0, and then f of q squared increases with decreasing q squared. Okay, the tricky part about this, which is weird, is that if you actually analyze the kinematics of this, you'll actually find that the square of the form momentum exchange is negative. Don't worry about that. You can get that by analyzing the kinematics. But that's the reason why this is being written as a function of minus q squared, because minus q squared itself is a positive number. It's just a detail. Okay? All right. What do I want to do now? Yes. Okay. So in the program of renormalization, which is discovering infinities and dealing with them, it's something of a two-step procedure. First, you have to find an infinity. Boom, there's an infinity. And the second step is to do what is called regularize. Regularize the infinity. And that means if you have a special infinity, you make it not special. No, that's not actually what that means. I'm making that shit up on the fly. No, so regularizing the infinity is a funny process. All you're doing is you're cheating. You're saying, I really, really don't want it to be infinite, so let's change it so that it's not infinite. Okay? So we could do that in a really simple way. Like we could actually say, the reason that's infinite is because we integrate to infinity. So why don't we not integrate to infinity?
I get to it stuff.
That's pretty baller.
I know, it's like, it's super, super awesome. Okay, so in this case, what we've done is we've imposed a momentum cutoff. We've said, I'm only going to integrate up to some value, in this case of mc squared. That's a very straightforward way to take something which is infinite and make it finite. It is by no means the only way to do it. There are many ways of taking infinite expressions and rendering them finite. One of my favorite is to actually formulate it in an arbitrary number of dimensions in Euclidean space, and then treat the difference from 4 dimensions as a small number. And so as that number goes to 0, you get back the infinity, but as long as that number is not 0, for example, you're doing the calculation in 4 plus epsilon Euclidean dimensions. As long as epsilon's not 0, you don't have an infinity. That's called dimensional regularization. There's also polyvalars. There's many different ways. But anyway, the point is you just use some scheme to make the thing finite. Okay? So with that in mind, we can now write down in sort of summary So what is our IQ squared now? So our IQ squared is this nice finite piece because we regularized it. So ln mc squared over me squared. And then we have this nice function f. And that's going to be minus qc squared over me squared c squared. Okay, so that's our I squared. And now we can add the contributions together to get m so far. So we'll have m tree plus m1 loop. Where this is not the only one loop diagram, but it's the only one I'm considering for now. Okay? So if we do this, and I'm going to take the expressions that I had earlier and kind of combine them in a nice way. We've got minus leading GE squared. We've got that first spinner sandwich that was common to both. And now we're going to have a new internal term, which has the contribution from the tree level and then a contribution from this one loop diagram. And if you're fading, you're like, I stood on my feet for 3 hours with senior design. You didn't even give me a chance to go get a beer. I hate you, flung on. You die, and you go to hell. Trust me, you're about to wake up. Because it's about to get interesting. Okay, so this is sort of a combination of all of these interesting pieces, rewriting, massaging, etc. Okay. Okay. Any questions about that expression?
Is that's M1 loop, right? That's not M.
This is M tree plus M1 loop. The tree term is if you ignored this whole hunk and you just took the one there. Yeah. I mean, look at what I wrote down for the tree term. It was this, 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 and then this.
Yeah, you're right.
Matt.
What is this M sub C?
It's M sub E. It's the mass of the electron.
On the integral, on the regularized thing.
A cutoff, mass cutoff. Sorry, C is cutoff.
Is there a reason we're not just calling that 0?
Say it again?
Is there a reason we're not calling that 0 then?
Calling what 0?
That you set the cutoff to the same as the lower limit, right?
No, this is Me, the mass of the electron
Oh.
squared, and that's mass cutoff squared.
Oh.
Sorry, my
Gotcha.
E's and my C's
Okay.
are getting dangerously
Okay.
close to one another.
Like getting?
Sorry. Okay, so here we go. So now what I want to do is I want to come back to this question of, okay, well, what are we measuring? What is this calculation useful for? Okay? So when we measure a process, we do not measure this. We do not measure this. Okay? We measure everything. And when I say measure, I mean literally. Experimentalists go and they put together experiments and they measure numbers. Okay? So you are always measuring the entire result. All infinite terms of the Feynman expansion. Okay? And then the way that you interpret your measurement is you say, okay, what these diagrams are going to do, and now I'm going to play a little fast and loose here, and then I'll come back and be more honest, if not at the end of the day, then tomorrow. But what you can say is, okay, if I go to higher orders, these diagrams are just going to get more and more loops, among other things. Okay, but at the end of the day, I could say I want to just measure an effective interaction that looks like this, where this effective interaction is taking into account the effects of all of these loops. That is exactly analogous to this, where you say, I'm going to ignore the truth of what's going on, and I'm just going to measure according to this thing coming in and coming out, and the results of your experiment are taking into account all of these little dipole pairs and their response to the charge that you put in the dielectric. Okay? But you interpret the result here in the same way that you interpret the result here. And you say, I measured the charge. It's just in this case, it's only an effective charge. In this case, it's the true charge. Okay? So now, to do this identification, we can actually do something really interesting, and that is we can define an effective coupling that depends on Q squared. And in the parlance of this description, we call it the effective coupling. And you could call it the effective coupling, but we use effective in a slightly different framework here. So this is normally referred to as the renormalized coupling. But we define a new coupling, which is the original coupling multiplied by this nice root. Okay? And you can think of this as the physical coupling measured at momentum transfer Q. That is, if we throw our electron in with some momentum Q, this is the effective charge coupling that electromagnetic coupling that we see. In the same sense here, if we throw the electron in with different energies, you're going to sense a different effective charge. Okay? Now, in terms of this new coupling, our expression for M just becomes minus GR Q squared times U bar 3, gamma mu, U1, eta mu nu, over Q squared, U bar 4, gamma nu U2. Okay? So this is literally what you would have written down if you were just doing a diagram like this. Okay? But this expression contains all of these loop contributions because we're working with this renormalized coupling. The actual diagram that looks like this has an expression in terms of GE itself. Okay? Isn't that interesting? You guys are way less impressed than I am. Okay, so first of all, this is an example of what we would call an effective theory. And that is, we're considering a simpler looking theory where we are choosing to not have to work with these sort of resolved, more complicated corrections. We're just taking everything that's happening and we're lumping it into, this is what we see, and then let's kind of write down a mathematical framework that describes what we see with the simplest possible diagram. Okay? Kowalski.
So there's two things happening here. There's the renormalization that happened in there somewhere, and then this is you writing in effect.
No. I technically haven't renormalized just yet.
Wait, even with the MC?
That was regularizing.
Oh, sorry, that was regular.
So what I'm about to get to the punchline, and this is where it's going to get deep, and where this is what I'm going after is going to make sense, hopefully. Okay? So just bear with me. So the last step in the formal part of this, before we get to the deep words behind it, is that you can now evaluate this expression. So let me back up and say operationally how you would do this. If I came to you and I gave you GE, and I said calculate this amplitude at a momentum scale Q, you would have to calculate all of these diagrams to get the answer. If I came to you and I gave you this value, and I said calculate this amplitude at momentum scale Q, this is all you have to do. So if you somehow know this value, you get to skip a lot of work. if you want to work in terms of this value, well, then you've got to do all this work. Okay? Now, just to sort of finish the detailed part of the story before we get into the interpretation, this is not the most convenient thing to work in terms of because it's a different value for every different Q.
Yeah.
So what we tend to do is we define the renormalized coupling at 0 momentum transfer. And so you can literally take this expression and say, okay, this is GE 1 minus. At 0 momentum, the F term is 0. Okay, so I just have this factor. Okay, and then there's a little bit of an approximation of what I'm about to write, but let's not get tied up in the details of it. If I utilize this, then I can write that the renormalized coupling at momentum transfer Q can be written as GR at 0 root 1 plus G squared R at 0 over 12 pi squared F of minus Q squared over 12. And it's 12 pi, yeah, 12 pi squared. No, it's in mean squared, C squared. I'm really not, I don't know why I'm carrying around all these factors. Okay, so what you can do is you can say, all right, if I hand you this GR of 0, then you can use this expression, because this is a known function of Q, to figure out what GRQ squared is. And then you can evaluate M using that GRQ squared using this one term. Remember, this expression has all of the loop contributions tucked into it. So now here's the important discussion we have to have. What is this? What is this? And what is this? Okay, so first of all, GE is the electron charge times the square root of 4 pi over h bar c. Okay? So really, GE is a measure of the electron charge. So we can swap out GE and electron charge, because these are just fundamental constants. Okay? So if I go to a book, and I say, hi, book. Knock, knock.
Who's there?
Knock, knock.
Who's there?
What's the fundamental electron charge?
What's the fundamental electron charge do?
Oh, I thought you were going to give me the answer. Okay, no, seriously. You go open up a book. Yeah, you go open up a book and you look up the value of the electron charge and it's a number. But where does that go in this story? Is that this? Is it part of this? Is it part of this? Where does that value go?
Anytime you see an E.
So my question is, so let's forget about electric charge for a second and just talk about coupling. If I measure the electromagnetic coupling, the fundamental electromagnetic coupling, am I measuring this thing, or this thing, or this thing?
Yes.
In fact, if you look up a number in a book where there's only one answer, it's definitely not this, because this depends on Q.
Yeah.
So that means it's either this or it's this, but which one is it?
The coupling has to be GR0.
Oh, the GR0.
Exactly. This is the thing that you look up in a book.
Wait, really? No.
This is the electromagnetic coupling at 0 momentum transfer. Turning that around, it's saying this is the electromagnetic coupling when you're really just performing sort of a macroscopic experiment. Because remember, the momentum transfer you can interchange with how close you're getting. So very large momentum is very small distance. Very small momentum, i.e. 0, is very large distance. The value of the electron charge or the associated coupling that you look up in tables and books is essentially measured at 0 momentum transfer. And that can be just like over a few centimeters. It's not like it has to be miles. Okay?
Cool.
Cool, right? Okay.
Yeah.
Well, here's the confusing part. Look at, so this is a value. What's the value? Somebody tell me the value.
1.602 times 10 to the negative 19. 19 coulombs.
Okay. Well, that's actually not G, that's the fundamental electron charge. Right?
Yeah, it's not like I'm trying to remember how I used to get your
My point is, listen, this is important. This is a number.
Yeah.
This is an expression which is diverging. Remember how we regularized that? We imposed a cutoff, but really and truthfully that was just so that we could kind of keep track of things, but this term is truly infinite. Okay? So we have something that it seems a little bit weird. We have a finite number, but it's expressed in terms of GE and an infinite number. Now what is GE? What is this thing right here? GE is what we would call the bare or fundamental electron charge or electric coupling. That is, if we could penetrate so close that we saw no screening from any of these virtual loops, if we could truly measure the fundamental charge of the muon that's sitting there, it would give a coupling of this value. And now here's the very important distinction between what I'm talking about now and what we talked about here. Here we said if you want to know the fundamental charge of the muon, you have two options, right? You can either just take it out of the dielectric, or you can hit it with an electron with so much energy that the electron gets closer to the muon than any of the polar molecules. Okay? You can't do either of those things in quantum field theory. You can't take the particle out of this bath of virtual loops. It's impossible. Furthermore, if you want to probe this thing with enough energy to see the bare charge, you have to probe it with infinite energy. So the mind shift that has to happen is the following. We built this entire theory in terms of this thing GE, which we kind of thought was going to be the electric coupling, which we kind of go and measure. But the truth is we built our entire theory in terms of a quantity that we have absolutely no access to. What we need to do and what we've done, and this is the important part of the story, what we've done is we've rewritten the theory in terms of a parameter that we can actually measure. And we can do calculations and compare to experiment. So what I'm going to propose to you is the fact that this is an infinity and this is finite is irrelevant because we don't actually know anything about GE. GE could be infinity. Who the hell knows? What we definitely know is that this is finite. So you can turn that argument around and say, well, if this is turning into an infinity, then GE has got to be doing something to compensate that. And there's no experimental way to determine that that's wrong. Okay? So the process of renormalization has two very important ingredients, and I'll just kind of summarize these and we'll end for today. It's got two very important ingredients. The first one is that the infinities that arise in quantum field theory, and these arise in a lot of different places. We're just seeing one example. The infinities that arise typically are associated with parameters that we can never truly know. And so if we actually relegate ourselves to degrees of, or parameters that we could actually go and measure, and write the theory in terms of those, then we typically find that the infinities disappear. That is a renormalizable theory. You take a theory with infinities, you write it in terms of something that you actually expect to correspond to measurable quantities, and if you can do that and have the infinities disappear, then the theory is renormalizable. The second incredibly important observation, which has nothing to do with infinities, is the following. If you are given this number, but then you're asked to do a calculation for a process at some q that's not 0, then you have to go and calculate the correct coupling to use. Because if your momentum transfer is not 0, this is not the right coupling. So you have to go and you have to, for example, use this expression. In a different process, you would have a different expression. Okay? So the idea is that in this program of renormalization, the coupling constants run with energy scale. For different energy scales on which you consider a process, you use a different value of the coupling. Okay? And this is a fact that I've alluded to a couple of times, and actually turns out to be a very interesting result in terms of the strong interactions. Now, to finish with one more sort of quantitative observation, we can just ask ourselves, this whole QED story is very, it's very abstract, lots of expressions. At the end of the day, are these little bubbles screening the electric charge of the muon? Or are they anti-screening? What do they do? Okay? And the observation is something like this. Yes. So where is it? Yeah, it's right here. Okay. So if we probe very far away, we just see G0, right?
Yeah.
So the question is if we probe closer, that is, we probe at some q squared that's not 0, then this is the coupling that we're seeing. And the question is this larger or smaller than G0?
Larger.
It's larger. Because remember, this function right here is increasing as we increase the magnitude of q squared. So we're taking 1 and we're adding something non-zero to it. So that means the closer we get, the larger the value of charge we're seeing from the muon. But that tells us that the virtual pairs were screening. Because screening tends to diminish the total charge that you see. Okay? That's a very important observation because when we apply this to QCD next time, we're going to find both screening and anti-screening together. Okay? All right, so that's it for today. I'll let you guys chew on that. I know that was a lot to think about and process. So come back next time with all your questions and hopefully we can get straight back.
Yeah, so